In this video lecture, I will discuss the method of post-doubled selection inference. In order to do so, we start with bringing back to memory a very old classical result for linear regression, the Frisch-Wald theorem or the Frisch-Wald-Lovell theorem. Suppose we have a regression model for y, regressing on x and on w. And we're interested in the coefficients of w, so we're interested in the vector beta w. Then we know, and that is what the theorem tells us, that either we regress y on x and w, so say on z, where z collects both, and we take out the last elements which corresponds to the w variables. Or we do partial regression, where we first regress y on x, and then we regress w on x, and we take the residuals and regress those on each other. So, more formally, we can define the residuals from the regressions of w on x, say w tilde, the residuals from the regression of y on x, y tilde, where of course here the deltas and gammas are just the least squares coefficients, and then regress those on each other, that's written here, and we get exactly the same outcome. So these two approaches tell us that they lead to the same outcome. Now this principle, which is very old and very standard result, is what this post-doubled selection method is essentially going to be based on. Let me briefly go over the proof just so everyone knows where this result is coming from. One thing we can simply do is we can just write out the least squares estimator. First of all, we want to get rid of this inverse, so we multiply both sides of the expression with z prime z. So you get z prime z times beta hat z prime z y. Well, you can write it out in blocks, so x prime x prime w, and so on. The same here on the right hand side. And now it's really only a matter actually of solving the equations. So I can take the first equation and then solve that for beta hat x. So I get this expression here and plug that into my second line, my second equation. So I take the second equation, I plug in beta hat x, and I start solving and rewriting. There's not much complicated going on here, it's just some standard least squares algebra. And I end up with the fact that actually my second part here, the beta hat w, corresponds to these the outcome of these partial regressions. Now, having said that, how can we use this for doing uniform inference? Well, what Belloni et al. Propose in a paper is to do something very similar in a high-dimensional regression framework. Particularly in that X be the high-dimensional matrix of regressors, and W is the variable of interest, which in their case corresponds to a treatment variable. So I'm going to refer to the variable of interest interchangeably as treatment variable. And then they do the Frisch-Wald setup. So they consider regression models. First, y on x and w on x. And rather than doing that, of course, with least squares, which is not possible because these are high dimensional, you do that with the lasso. And you just do the lasso or the adaptive lasso or whatever variant you want. You estimate these regressions. And then, this is the crucial step, you collect all the variables which are selected. So you create these sets, S hat gamma and S hat delta, which contain all the variables that were selected in these two regressions. Now the second step is actually then very easy. The only thing we have to do is we take the union of the variables that were selected in our two regressions, call that thing as hat, and then we're going to do a final regression of y on w and on the selected variables in x. Right, so we count which of the variables were selected in at least one of these initial regressions, collect those and put them in your final regression. And now the cool thing is, this you can just do with least squares. And not only that, you can do that also doing inference just based on least squares. So you do standard least squares, standard errors can be used, and you can construct hypothesis tests and confidence intervals in the usual way. And this is valid. Well, and this is all there is to the post-double selection procedure. So it's quite funny that in a way we found an extremely simple solution to a very difficult problem. Now let's see why this works and why this what's the intuition behind it. So to make it a bit more manageable, I'm going back to the case where we have just two regressions. Now x1 is the first one is going to be the variable of interest, say our treatment variable, and x2 is going to be a control variable that we don't know if we should include it or not. So this is essentially the case that I looked at last week when I explained the problems with omitted variable bias and how this affects the properties of model selection. Well, we take a simple setting where there's some correlation rho which determines how the correlation is between x1 and x2. And well, as we did last week, we said, well, what if you accidentally leave out x2? What is the consequence of that? Well, then of course your error term now contains also the contribution from x2, and if rho is not equal to 0, then your new error term through x2 is going to be correlated with your regressor, creating an endogeneity problem, and therefore we get an inconsistent estimator. This is what we showed last time. So how does this post-double selection method allow us to avoid that problem? Well, let's have a look at another step that we take, and that is regressing y on x2 only. Well, you can write that out, of course. What you will get is exactly the same as we have here, where we did y on x1, but then y on x2. So here, of course, all the 2's and 1's just change. Of course, that's again inconsistent, and it again depends on beta 2, beta 1, and rho, and of course the ratio of the standard deviations. Well, the same thing we can do for another combination that we can do, and that is doing x1 on x2. Well, here of course we don't really have a regression model for x1 and x2, but we can easily see what the regression will converge to, because if I define my regression coefficient in the standard way, I can just look at the limits of these things, and I see that what we're getting here, if we divide by 1 over n, is going to converge to the covariance between the two, which is rho times sigma 1 times sigma 2, and here dividing by n is going to make this convert to the variance. Well, if you cancel these out, you get rho times sigma 1 over sigma 2. And now, if we realize what post-double selection is doing, well, it's essentially doing these two regressions first. We'll take y on x2, and we take x1 on x2. Of course, in this particular case where there's only one variable, things are, of course, easier, because you could just do least squares. But think about this in a model selection framework. So suppose that you would not do least squares, but you would do a lasso regression. And when would you then select these variables in your model? Well, if your coefficient, of course, is going to be far away from 0, far enough away from 0. Well, this is, in essence, this is the coefficient that we're aiming for, right? Because, of course, we're having an inconsistent model, but still, would be the true regression coefficient of y on x2, and this would be the true regression coefficient of x1 on x2. So when does the lasso select x2 in the first regression? Well, whenever this coefficient, beta 2 plus beta 1 times rho sigma 1 sigma 2 is large. When would the lasso select x2 in the second regression? Well, when this coefficient, rho times sigma 1 over sigma 2, is large. So if we take the union of those, because that's exactly what we're doing in post-double selection, when would we then not select x2? Well, only if they are not selected in either. So that means that both this one must be small and that one must be small. Now, when will it happen? Well, the regression of x2 of x1 on x2 is the coefficient has this form. Well, the variances will be fixed. They will not, of course, not be 0 or infinity. So the rho is going to determine that. The rho is the correlation between x1 and x2. So this is only small if the correlation between x1 and x2 is small. So if rho is small. Well, but if that is small, when is this thing going to be small? The coefficient of y2 on x2. Well, if rho is going to be small, this part will become small. So that means beta 2 must be small as well. So you can only end up with not selecting x2 if both rho, the correlation between x1 and x2, and beta 2, the coefficient of x2 in the original regression, are both small. Now, if both are small, if that's the case, and we would not select x2, what is the consequence of that on the omitted variable bias? Well, and then if you look at this coefficient that we would be converging to in the restricted regression, only x1, well, rho small, beta 2 small, you multiply them so they become even smaller, become small squared. And then, in that case, this coefficient will just be beta 1, and we don't have omitted variable bias. So what we're really doing with this post-double selection is looking at the two conditions that we need for omitted variable bias. There is either omitted variable bias if rho is large, so there is a correlation between x1 and x2, or if beta 2 is different from 0, if that is relatively large. So x2 matters in the regression. And we're checking both things here with these initial regressions. We're checking first by doing x1 on x2. Well, is there correlation or not? And we're also checking, is beta 2 important or not? And while obviously we know that the lasso can make mistakes, that is what we know. Well, because that's of course the whole problem why it does not deliver uniform inference. But we check both, and we only kick x2 out if both of our checks actually fail to find non-zero coefficients. And because we do that, and it works with this multiplicative effect, we can reduce the omitted variable bias to such a small level, say small squared, that it will not affect our estimation anymore. So let's do this a bit more formally to see what we get. Well, again, this is our restricted estimator, right? But we only regress y on x1. We can split that in these two parts. Well, this is the part that, of course, we get the normality from, and this is the part which creates the bias, which has, again, this covariance term between x1 and x2. But also is multiplied by beta 2. So if this would go to 0, and note that we've already multiplied it here by square root n, which is why we have an n minus a half factor, which was the problem before. Well, if this goes to 0, then, of course, there's no omitted variable bias, and we don't get a wrong distribution. Well, given that we have this covariance between x1 and x2 of this form, we can actually write down a regression model for x1 given x2 with that particular coefficient that we derived before. Now let's look at this term in more detail. So take that term and use this regression expression that we had for x1, and we write things out, and you see that what you get here is x2 times x2, so x2 squared. So that part will cancel with this sum here, and we're left just with this part here. And we have the error term, if you want, that we created, the eta. And we know that actually this eta times x2 means 0 by construction. So we have square root n times some coefficient, so that's obviously going to be problematic. Plus this term here, which is going to be, could of course also become problematic because, well, it converges to something like a normal. Now let's see what we get if we take small parameters here. Right, where we take small parameters, well, only if the parameters are small enough, that's what we've also seen last week, they will not be detected by the lasso. So take them large, of course they would yield massive problems because you get square root n times something large. But that kind of cases will get picked up. So we need them to be small. Well, I'm going to go again in this range, small, say Cn going to 0, but Cn times square root n going to infinity. Plug those in for rho and for beta 2, because we know that actually we need both of them to be in the range where the lasso cannot really detect them. Now we need a tiny bit more here, and we need that also that Cn times n to the power 1 over 4 goes to 0. Right, so we're going to make it a bit more than just Cn going to 0. Well, this we can achieve, but we have to make sure we choose the tuning parameter appropriately. And now we can plug those into this expression. And in particular, we have to realize, of course, that what the expression that we had was multiplied by beta 2. So here I have it without beta 2. But if I go back one more, I have it actually multiplied times beta 2. And so I get something small here from beta 2, and I get something small here through this covariance term. So I get a term Cn squared here. One Cn coming from beta 2, one Cn coming from rho. I also get another Cn in front of this term which had this normal distribution. Well, and then we can see a couple of things. First of all, this term will go to 0 because Cn goes to 0. But even more importantly, this difficult term, the one which has square root n in front, it will also go to 0 because we know that n to the power 1 over 4 times Cn goes to 0. So because we have a square here, we have enough smallness here to kill off this square root n term. Of course, this only happens if both beta 2 and rho are small, because only that gives you this square. But that is exactly what we are looking for by doing two initial regressions. Because if one of them would not be small, then one of these two initial regressions will pick it up. Now, only if they are both small, there's a chance that they will not get picked up. Well, but if they are both small, they are harmless because they are small enough to get rid of the omitted variable bias. So this is the idea behind the post-double selection method, and therefore it makes a very simple way, if you want to do inference on one particular variable, a very simple way to actually do that in an appropriate, valid way. Now what they actually in the paper consider is a slightly more general setup, and it's very similar to what I've discussed before. And what they say is, well, we don't necessarily have to assume that these axes, that there's a linear relation between y and these axes. Maybe there are some other variables, u, say a small number of them, perhaps, maybe large, maybe small, q, and there's some possibly nonlinear function which we don't know the form of. Now what they're saying is, well, maybe instead of this u, we could just approximate this function with a linear function of axis. Well, of course, there are many different ways you can think about this. One would be simply be actually the u are high dimensional but linear. Another thing would be that these x's are, say, polynomial transformations of these u's. And therefore you could capture general forms of these functions j, g, and h of u. Now, that is of course the crucial assumption that they make, that actually you can choose appropriate axes which may consist of these u's or may not, and may be transformations of these things. But either way, if we can approximate this with a relatively small approximation error, Rg, and for the same we do for h, if we can approximate that with a relatively small approximation error, then we can write down this linear model that we started actually off with. Now, we also need that, of course, that our betas and gammas here actually are sparse. And if those are sparse, well, in that case, then we can do this approximation in a way that these errors are small. And we can use the lasso or related method to actually do model selection on them. So that means that you also, again, there might be linearity, but, well, linearity, you should also not take it too literally. Now, just if you want to read the paper, you'll see that they actually do a slightly different version of the lasso. So they have some data-dependent penalties here, which also can, for instance, incorporate heteroscedasticity. And that makes the method a bit more efficient. So there's some differences, but this is not crucial for how the method works. Also, another thing that you would encounter if you read their paper is that they don't do selection via cross-validation or information criteria, but they actually have a plug-in rule where they plug in a fixed value of lambda. But again, this is not essential to why the method works as it does. And indeed, what they also show is that, well, you don't even need to do a lasso kind of estimator. You could do any kind of model selection estimator, including standard old-fashioned model selection in low-dimensional cases, and it still works. So the post-double selection idea is actually much more general than just the lasso. Now to round up this part, let me have a quick look at the simulations. And I'm going to do the same simulations that I did last week, where I showed that the lasso did such a poor job of constructing confidence intervals. So I'm going to do a linear model. I'm going to say my beta 1 is equal to 2. Everything for j equal 3 or higher is 0 for beta. And beta 2 varies between 0 and 2. I'm going to do BRC selection. And I have 10 variables only, so it's not very high dimensional. And I take 50 or 100 observations. X1 is my treatment variable, the variable of interest, which I'm going to do inference on. And the others I'm going to do selection on. And now I'm going to compare constructing confidence intervals for beta 1 using either the oracle property, where we just ignore the whole model selection issue, or we do post-double selection. Well, this is the same graph as we had last week, or we had least squares, just the black line here. We have lasso, adaptive lasso, and post-lasso, which have this bump here, where they really, for smallish beta 2s, where they have this problem that the beta 2 is large enough to cause omitted variable bias, but not large enough to be selected. And then we have the post-double lasso and the post-double adaptive lasso. Now you might wonder where they are, because you can see them on the graph. Well, the reason why you can see them, if you look carefully, you see that they are spot on the 95% coverage probability. So it completely solves here your problem. Now to check if that really keeps on working, let's look at cases where things get worse. So we take rho equal to 0.8 here. So this, of course, creates a bigger problem, right, where coverage is dropping below 60% for the lasso methods. Still, the post-double selection methods work perfectly. Well, take n is 100, where you got this even sharper but narrower drop here. Well, again, the post-double selection methods keep on working fine. They're even slightly better than least squares. Now, look at the final case that created such even bigger problems, dropping coverage to 30%, where we only have x1 and x2 correlated. Well, again, there's no way to disturb the performance of the post-double selection methods, whether you do the lasso version or the adaptive lasso version. So yes, it does exactly what it should. It completely eliminates the problems that we had with the standard lasso inference, and that with such a very simple trick. Now, of course, you might wonder, well, are we done then already? Well, that was a very quick final lectures. Well, of course, there are limitations to this method as well. Not so much in terms of the theory. I mean, the original paper does look already at things like heteroscedasticity and non-Gaussianity, so that all works. They don't consider cases where there's dependence and Well, the dependence case is more complicated, of course, but actually there are several recent papers which have established validity for time series. In particular, one paper that I wrote together with my PhD student, Luca Margheritella, where we show that for VAR models, actually, you can do the same trick, and it's also there. That is also valid. Another thing to think about is that actually, and that's still a bit, well, we don't really know how to think about that, but it relies on lambda not being estimated from the sample. The theory works for a fixed lambda. But actually, we also estimate lambda from the sample. So it's another model selection step. Well, apparently, if I go back to my graphs, it does not seem to hurt that much because it seems to work fine. But still, it's a kind of a limitation we should keep in mind, that there is actually another layer of model selection that we're not taking into account. Now, I think the biggest limitation is actually the bottom one, and that is really designed for a single parameter. You can repeat the method for different parameters, right? Suppose we would do inference here also on x2. You could do, well, first x1 and then x2. It does not really give you, it gives you marginal distributions, which is not great. Now you can do it actually with more parameters. That's also what we show in the same paper. If you have k parameters that you want to do inference on at the same time. For instance, what we do in the VAR is test Granger causality, where you do inference on the coefficients of all lags of one variable and another. That works. You can do the method in that framework. But what is complicated is you have object of interest, which depend on many or all parameters. So for instance, you can think of prediction intervals. The prediction, of course, depends on essentially it's beta prime x. So these are all your betas in there, or general testing combinations of parameters, or something like impulse response functions, which are nonlinear functions of all your parameters. So that is, of course, complicated, and there's not really a solution to that. The exception is if you can express your tests or your inference on the many parameters as something talking about the maximum over all these parameters, or the maximum over the absolute value of these parameters, then actually you can do, and that is covered in this paper by Belloni et al. So to conclude, we actually found a very simple trick to do quite powerful inference. It doesn't cover everything, but at least we can get quite a long way with this method. Now, as you can imagine, it's not the only method we can use. There are alternative ones, and those ones will be discussed next.